In this lesson, we will delve into the principles of gear machining and tool technology in Project 1, with a particular focus on Task 1.1, Gear Machining Methods. We will provide a detailed introduction to various gear machining methods, including the forming method and the generating method, exploring their principles, characteristics, and application scenarios. Additionally, we will analyze the precision mechanical design concepts inherent in classic machining methods such as gear shaping and gear hobbing, appreciating the charm of traditional techniques and recognizing them as the foundation of modern manufacturing. Students in the field of mechanical manufacturing gears are extremely important components widely used in various mechanical equipment such as automobiles and machine tools. Gear machining methods are crucial for ensuring the quality and performance of gears. First, let's understand the classification of gear machining methods, which are mainly divided into the forming method and the generating method. The forming method involves using a forming tool that exactly matches the shape of the gear tooth slot being machined to cut the tooth profile. Common examples include gear milling and gear broaching. Gear milling is performed on a milling machine using either a disc-shaped gear cutter or a finger-shaped gear cutter. Disc-shaped gear cutters are typically used for gears with a module M is less than or equal to 10 and a relatively narrow tooth width. Finger-shaped gear cutters are often used for situations where M is greater than or equal to 10 or the tooth width is particularly large. The principle of gear milling is quite simple. The cutting edge of the tool matches the shape of the gear tooth slot, and the tooth profile is machined through the rotation of the tool and the linear movement of the workpiece. For instance, when using a disc-shaped gear cutter to machine a gear, the tool rotates around its own axis, while the workpiece performs a linear feed motion along the axial direction. The advantages of gear milling include simple equipment, low tool costs, and the ability to perform machining on a standard milling machine without the need for specialized gear machining equipment. However, the drawbacks are also evident. The machining precision is low, and the production efficiency is not high. This is because for gears with the same module, the tooth profile curve varies when the number of teeth differs. In actual production, to reduce the number of tools, typically only 8 or 15 cutters are equipped for each module. Each cutter can only machine gears within a certain range of tooth counts, so the resulting tooth profiles are approximate and have a certain degree of error. Gear broaching is performed using a broach on a broaching machine. The teeth of the broach match the shape of the gear tooth slot, and the metal in the tooth slot is removed through the linear motion of the broach. Gear broaching offers relatively high machining precision and production efficiency, but the manufacturing of broaches is complex and costly. Additionally, a single broach can only machine one specific gear specification, making it suitable only for mass production. The generating method is a gear machining technique that utilizes the principle of gear meshing. The tool and the workpiece simulate the meshing motion of a pair of gears or a gear and a rack, and during this motion, the cutting edge of the tool gradually envelopes the gear's tooth profile. Common generating method processes include gear hobbing, gear shaping, and gear shaving. Gear hobbing is a process that uses a gear hob to machine gears. The gear hob resembles a large helical gear with its cutting teeth distributed along a helix. When the hob rotates, it is equivalent to an infinitely long rack moving. The workpiece and the hob rotate in accordance with a specific transmission ratio, similar to the meshing of a gear and a rack, thereby machining the tooth profile. Gear hobbing has many advantages, including relatively high machining precision, generally achieving 7 to 8 grade accuracy. It also offers high production efficiency, making it suitable for mass production. Additionally, gear hobbing can machine spur gears, helical, cylindrical gears, and even worm wheels. Motion analysis of gear hobbing. During gear hobbing, there are primary motion, indexing motion, vertical feed motion, and additional motion. The primary motion is the rotational movement of the hob, which is the main source of cutting force. Indexing motion ensures the strict transmission ratio between the hob and the workpiece, expressed as N workpiece divided by N hob equals K divided by Z workpiece, where N hob is the rotational speed of the hob. N workpiece is the rotational speed of the workpiece. K is the number of hob starts, and Z workpiece is the number of teeth on the workpiece. Vertical feed motion is used to machine the entire tooth width, allowing the hob to move linearly along the axis of the workpiece. Additional motion is required when machining helical cylindrical gears to compensate for the influence of the workpiece's helix angle. Gear shaping is performed using a gear shaper cutter. The gear shaper cutter resembles a gear with its teeth having cutting edges. During gear shaping, the shaper cutter performs a reciprocating cutting motion while engaging seamlessly with the workpiece, thereby enveloping the tooth profile. The advantages of gear shaping include the ability to machine special gear structures such as internal gears and compound gear assemblies. Additionally, gear shaping offers relatively high machining precision, generally achieving 7 to 8 grade accuracy. The motion of gear shaping also includes primary motion, indexing motion, circumferential feed motion, and radial feed motion. The primary motion is the reciprocating up and down movement of the shaper cutter. Indexing motion ensures the strict transmission ratio between the shaper cutter and the workpiece. Circumferential feed motion involves the rotation of the shaper cutter around its own axis. Radial feed motion is the movement of the shaper cutter towards the center of the workpiece, used to gradually cut to the full tooth depth. Gear shaving is a finishing method for gears, typically performed after gear hobbing or gear shaping. The shaving cutter is a high-precision helical gear with many small grooves on its tooth surface, forming cutting edges. During gear shaving, the shaving cutter and the workpiece engage in a free meshing state, and the relative sliding between the tooth surfaces removes small amounts of material, thereby improving the gear's precision and the surface quality. Gear shaving is primarily used to enhance the tooth profile accuracy and the tooth alignment accuracy, as well as to reduce the surface roughness of the gear teeth. Under ideal conditions of pre-shaving accuracy, allowance, and machine conditions, gear shaving can typically improve 8th grade accuracy to 7th grade and 7th grade to 6th grade. Further improvement requires gear grinding or honing. In classic machining methods, such as gear shaping and gear hobbing, there is a wealth of precision mechanical design concepts, such as the principle of generation. The invention of the generation method is the crystallization of craftsman's wisdom, cleverly utilizing the principle of gear meshing to machine precise tooth profiles through the relative motion between the tool and the workpiece. This method not only enhances the precision and efficiency of gear machining, but also lays the foundation for modern gear processing technology. From a historical development perspective, traditional gear machining processes have undergone long periods of practice and improvement, continuously being refined. These traditional processes are the cornerstone of modern manufacturing, and we should inherit and promote their essence. In learning and practice, we must deeply understand the principles and the design concepts of these classic machining methods, continuously innovate, and combine traditional processes with modern technology to advance the development of gear machining technology. In automobile manufacturing, the quality of gears directly affects the performance and reliability of the vehicle. The transmission of a car contains numerous gears, which are typically machined using gear hobbing or gear shaping methods. For instance, a certain automobile manufacturer uses gear hobbing to produce transmission gears with high precision requirements, ensuring the accuracy and strength of the gears. This results in smoother gear shifting and reduced noise during driving. For some internal gears, gear shaping is employed to meet the requirements of special structures. In this lesson, we primarily studied gear machining methods, including the forming method and the generation method. The forming method includes gear milling and gear broaching. Gear milling is simple in terms of equipment but offers low precision, while gear broaching provides high precision and efficiency but comes at a higher cost. The generation method includes gear hobbing, gear shaping, and gear shaving. Gear hobbing has a wide processing range and high efficiency. Gear shaping is suitable for machining gears with special structures, and gear shaving is a finishing method. Additionally, we explored the principle of generation inherent in classic machining methods, such as gear shaping and gear hobbing, appreciating the charm of traditional craftsmanship and the wisdom of artisans, and recognizing that traditional processes are the cornerstone of modern manufacturing. I hope everyone will further consolidate the knowledge learned after class and deeply understand the principles and the characteristics of these machining methods.